right, can we get started? Great. Good afternoon, and welcome to I/O 313. There were a lot of amazing product announcements this morning, and hopefully you noticed that committed use discounts can be used with Container Engine, and now you can use Spanner and PostgreSQL also in your applications with Container Engine. There were not a lot of Container Engine related announcements, and that's what this talk is for. We're going to be talking about some of the latest features that are coming up in our next release, which is due in early April. So some of this material is roadmap and subject to change, but we're excited to share with you a preview of some of the coolest features that are upcoming. So one of the highlights of working in technology is when you're building a product that is used by other products that you love. And that's been the case for me with Philips Hue. Kelsey and I, of course, work on Kubernetes and Container Engine here at Google, but we're delighted to be joined by George Yanni, who is an inventor of Philips Hue lighting. This is IoT-connected lighting. I've been working with George for the last 2 years in a close collaboration with Google. But even before that, I had bought Philips Hue lights, and I have them installed in both my living room as well as my kids' bedroom. And they love the colorful lights at night, and especially on holidays like Halloween. And now, knowing that Philips Hue light is powered by Google Container Engine, a product that I helped build, makes mommy very cool. So it's not just Philips, though. You might be surprised by how often you are using Kubernetes. I'd like to do a quick show of hands here. How many of you have recently played, a hit mobile game, or shopped at one of the world's largest retailers, or followed breaking news, or attended a concert? And then I put the last one in here for the workaholics amongst us. How many of you have filed expenses recently? Anyone who hasn't done any of these? I think those people have been busy making contributions to the Kubernetes open source code base, so they haven't done any of these. But as you can guess, all of these services are running on Kubernetes today. That's just a small sampling. So you might ask, why is this the case? I think there are 3 reasons. Number 1, speed. And here I'm talking about developer productivity. These are quotes from some of our users. They've moved from commit to production in minutes. And they do that 20 to 50 times a day. That's number 1. Number 2, scalability. And here it's really efficient scale out. So Pokemon Go was the fastest app to $1 billion, and Kubernetes was behind the scaling of that app. Also, Black Friday demand, Home Depot talked about it in yesterday's keynote, also powered by Kubernetes. And what tends to happen is that then becomes the new standard. When a technology becomes this commonplace, everyone expects all applications to be able to meet this type of scalability and this type of development speed. And last but not least is open. So you can use Kubernetes anywhere, whether it's on Google's cloud or it's on your premise. And Walmart is a very nice example of that. Walmart are using Kubernetes in their logistics warehouses, 200 of these warehouses. These are small IT closets almost, with VMware on them, and they're running Kubernetes on that. And of course, there are many that are using it on Google Cloud as well as on AWS. So that flexibility is something that hopefully many of you value. But there's nothing better than hearing about an actual deployment from an actual user. What's it like to use Kubernetes on Google's cloud? Is it easy? Is it secure? Is it reliable? So for that, I'd like to, without further ado, welcome George Yanni to come up on the stage and talk about Philips Hue and how they're using GKE.
Thank you very much, Aparna. Now, I work for Philips Lighting, and we're actually the largest lighting company in the world. And I think it's almost certain that every single person inside this room has actually experienced some of our products. Whether it's in our homes, under the streetlights, which light our roads, or admiring one of the thousands of monuments like San Francisco's Bay Bridge, which we actually do the lighting for. Now, Philips Lighting is really driving for a change in the lighting industry. And that change is really to tap into the value that lighting being ubiquitously all around us can potentially bring. There is nowhere where we work, travel, or enjoy ourselves which isn't underneath multiple artificial light points. And we think that by making those light points more intelligent, we can make the world more personalizable, easier to manage, and easier to monitor. Now, our answer for this transformation in the consumer space is my product, Philips Hue, which I've been working on for the last 5 or 6 years. It is one of the most popular smart home products, and we really believe that by making lighting in our homes more connected, we can really transform what it does in our lives. I believe that lighting can be an alternative to having a guard dog at home, by making it seem like you're at home, even when you're on vacation. I believe that lighting can be an alternative to your morning cup of coffee, by tapping into the way our bodies react to warm and cold light. I believe that lighting is an alternative to painting your walls, by letting you change the look and feel of your rooms multiple times a day to suit different activities. I even think that in the future, lighting will be an alternative to surround sound speakers, by having your lights synchronized to content on a TV screen and bring the explosions or the forest into your entire room in synchronization with what's going on the screen. And we can do all of this by making your lives more comfortable and convenient. There is untold potential for smart lighting to change how we live our lives. Now, why do we actually need a cloud solution to do all of this? And actually, right from the beginning of Philips Hue, we designed a cloud backend for our solution. And we actually designed it not as the primary way. We focused as much as possible to actually happen locally inside the home, to keep latencies as low as possible. But we always said we need a cloud backend, and we need it so that we can let people control and monitor their homes when they're away. We need it so that we can keep all of our products up to date with the latest features and security updates. We need it so that we can learn from our consumers how people are actually using this product so we can make it better over time. And we needed it to be able to integrate with other cloud services and platforms that are out there to realize new use cases. Like, for example, with If This Then That, where we can have your lights flash when your favorite sports team scores. Now, we also have some particular needs that drove our choice and design for a cloud solution. One of the most important things to us is the incremental cost per new home we serve. And this is because all the cloud services for Philips Hue, we bundle as a free service when you buy your first Hue product. That means the lifetime cost to offer these services towards that customer have to be bundled in the bill of materials of that product. So in order to keep our products as affordable as possible, we are obsessed with making that cost to offer this free service as cheap as possible. And it's really this incremental cost for every new user. Another thing which really drove us, especially at the beginning, was Philips Hue, when we launched it back in 2012, was really a new-to-world product. And frankly, a lot of people thought we were a bit crazy making a $60 light bulb you could connect to the internet. Now, we believed that this would become a huge thing, but we didn't know how fast it would. We didn't know if this was going to be a very slow ramp up or something that took off immediately. And we really risked, in building this cloud backend, that we had a solution which either had the potential to kill this small idea early on by lumbering it with expensive infrastructure and operations costs, or on the other side, that couldn't actually keep up if the market did explode. That's one of the major reasons we came to Google Cloud already and built our first infrastructure on Google App Engine, because it let us pay for what we needed and let us actually scale when, luckily for us, the market did explode and continues to explode. And we've actually had a very surprisingly pleasant journey in scaling our solution multiple factors every year. Another thing, we're not a cloud company, we're a lighting company. What we do and what drives us is to offer the best possible lighting use cases and experiences to consumers. And that's where I want to spend my engineering money. So I don't want to have to spend all of my engineering money on keeping infrastructure up and running. So I really wanted a solution which let me focus on actually building our use cases out and not having to worry about maintaining and running infrastructure. And finally, and this one is actually a bit new and wasn't something we had in our mind at the beginning, is latency is super important. When we first designed all of this, the idea was, okay, you're controlling your lights from outside of home to, update your schedules or, check that you haven't left the light on. It doesn't matter that it takes a few seconds to do that. But what's happening more and more is other smart home products are entering your home, which are cloud-centric. All of their logic, intelligence, APIs are sitting in the cloud, and so we integrate with them also in the cloud. So an integration like what we have with the Google Voice Assistant, that actually goes up to the Google Cloud for the voice processing and then pokes our cloud APIs. And this is something you're doing inside your home. And if your lights take more than a second to turn on, that feels really slow. So we have a new, renewed push to actually get our cloud latencies down as much as possible because it's actually being used for real-time use cases inside the home. Now, we have a very broad and rich partnership with Google. And it's one of the great things about actually working with Google. We use a broad variety of their products. We use a whole suite of products from their cloud platform together with Apogee to actually build our cloud backend. We build our own Android app and have hundreds of other apps built with our lighting APIs running on Android and Android Wear. We were one of the very early Works with Nest partners, letting us offer use cases to, for example, react when a Nest Protect smoke alarm detects smoke by setting your lights to a dim red color, which actually helps you see better through white smoke conditions. And we were also launch partners for Google's new offerings in the smart home space with Google Home, Google Assistant, and Google Wi-Fi, where we also have great integrations. So there's a lot of touch points with Google, and we really work across the company to achieve our mission of letting people use lighting in a richer way. So what does this actually look like? So this is a snapshot, a very cloud-centric snapshot of how the Hue architecture looks. And we'll go through what happens with a simple command. Let's say you've taken out your Android phone and you've asked Google Assistant to turn off your lights. Something that happens maybe not millions of times a day, but lots of times a day. What that will do is that will initiate a client request using our API to turn off all lights inside the home. That goes initially towards Apogee, which is our entry point towards the cloud for clients, which will check that that application has the right permissions to use the APIs it's requesting and is within its quotas. That then gets passed on to a set of Kubernetes pods, which we call Client Eastward. These are the pods which handle all of our clients' requests. They process that request, and then they forward it on towards the appropriate pod, which is handling the connection towards that particular Hue home that's being addressed. And we do that forwarding via a Redis instance that's running on Compute Engine. Now, we actually have two different ways of interacting with Hue homes, and that's because we're in the process of transitioning towards a new lower latency solution. So the legacy mechanism, which will stay relevant for a good time yet, is Golden Gate. And this you can think of effectively as a message queue, where all messages for bridges to process are stored, and it can be polled by bridges when they're triggered to do so, to actually fetch and process these messages. The new solution that we've come up with, we call Freddie Mercury. And this actually maintains permanent open WebSocket connections towards every Hue home concurrently 24/7 in the world. And by doing this, we are actually able to push messages directly into the homes with extremely faster latency, so we can actually get much closer to real-time performance inside the home. And we're rolling out support for this capability towards bridges around the world as we speak. Now, this Freddie Mercury pod actually, we needed to develop a new custom autoscaler to be able to get that to work and scale reliably, because we actually run into limits of number of open connections on these pods before we hit any memory or CPU limits. So we have a custom autoscaler that's doing that. Now, via either of those pods, a message will eventually arrive into our bridge, which is a central device we have inside the home that manages the lighting network inside the home. That bridge will process it and then initiate a Zigbee Lightlink radio broadcast inside the home, which will be picked up by all of the lights, and then they will turn off. And if we've done our job right, and we're using our new fancy service, all of that should happen in less than a second. So this is what it takes in the 2017 to turn off a light bulb. Next to that, we have a bunch of other services. We have a front end where users can create and manage accounts, monitor their homes, which is actually built largely on App Engine, as well as a few other things. We do a lot of our logging and analytics in Datadog, which gives us a really great overview and snapshot of everything that's going on within our infrastructure. So this is more or less how the Hue Cloud is looking today. So how's it actually been using Google Container Engine in production? I think the first thing is we've really enjoyed using the technology. It's really given us the right balance between freedom to actually optimize and design our systems for our particular needs that we didn't have with App Engine. But it's also not given us too much additional overhead and burden in terms of actually running the system. And it's really given us the confidence to go all in with small microservices that we can run at scale, allowing us to actually develop and launch much more quickly because we have much better separation of concerns. So all in all, that's good stuff. We're focusing on features, we're developing faster, we're scaling without having to worry about infrastructure. It hasn't been without pain points. It was quite some work to actually make the transition from App Engine towards Kubernetes, and some of the challenges that we've had have been particularly around the logging infrastructure around GKE, where we had quite some issues in terms of getting reliable logging out of the system when pods were being used intensively and we were developing, so putting a lot of logging in to understand what was going on. These things are now largely resolved, but it did make some of the issues that we faced early on a bit more difficult to diagnose. Another thing, something that we're focusing on more, is lower latency. So we're looking at how we can actually have our infrastructure replicated in more places in the world just to get latencies down so we don't have to cross the Atlantic so often. And that's something that we've been reluctant to do up to now because it will increase the amount of operational overhead that we have. And my developers say no when I tell them about that. But all in all, it's been a great experience, and we continue to enjoy working with Aparna and the rest of the Kubernetes team. Do you want to come back up?
Thank you, George. That was great. So, we have some features in our upcoming release. In fact, Philips is looking to go to multi-regions with their deployment to lower latencies in other regions as well. And we have some features coming in our latest release that should help with that. And while specific features are important to specific customers, I think one thing that is important to all customers is our velocity. This chart is showing we have had a consistent release of Container Engine and Kubernetes every quarter over the last year, and we're going to continue that. So the good news is that if there's a feature that didn't get in this week, it'll likely be there in 12 weeks. And you can contribute to this project, including, contributing to the code, but also contributing use cases and what you'd like to see in the features roadmap. So each release is not just an effort of Google engineers, but also our community of users and the broader community of companies that work on Kubernetes. And overall, more than 442 years of effort have gone into Kubernetes and Container Engine. So now let's talk about our upcoming release and what are the features that we'd like to preview today. As a reminder, this is roadmap, so this is subject to change. First and foremost is scale. Scale tends to be important to a lot of you, and Kubernetes will be announcing support for 5,000 node clusters in the upcoming release at the end of this month. That means that a single Kubernetes control plane will be able to control 5,000 nodes, 5,000 VMs in the case of Container Engine, and up to 30 pods per node, so that gets you more than 100,000 pods per cluster. That's a fairly large cluster. You can put a lot of services into that. And along with that, we will have sophisticated scheduling, some of which I'll talk about, and sophisticated multi-tenancy features, which are on the roadmap as well. Here's kind of the history of scale. It was particularly important to Pokemon Go that we were working on this when they came along. And as you can see, Kubernetes and Container Engine started at a humble 100 pods per node, and over the last 2 years has now scaled up to 5,000. Every time, the metric that we've used to measure scale is the same, which is that 99th percentile API latency is less than 1 second, and the 99th percentile pod startup time is less than 5 seconds. And this has been tested in our environment and verified for 5,000 node clusters, and we look forward to supporting production applications on this. So, much more practically, scale is a good thing, but you're not necessarily going to manually scale to a large number. A lot of customers use auto-scaling, and George mentioned that they use auto-scaling. There are two types of auto-scaling in Kubernetes and Container Engine. One is horizontal pod auto-scaling. This has been around for a while. It's very easy to set up. You can configure it for a replica set or a deployment. And you basically use this command line. You set a minimum and a maximum in terms of the nodes that you want. And currently, the target that the system optimizes for is CPU utilization. This is not always the thing that you want to optimize for. So one of the roadmap items we're working on is built-in support for custom metrics. This is something, though, that you can do today. And as George mentioned, they are using number of WebSocket requests or the queue length as a custom metric to feed into the autoscaler. So that's something that you can do. It's not a feature yet, a fully supported feature yet, but many people do use it. And that's one of the beautiful things about Container Engine and Kubernetes is the ways that you can customize it. The second feature on auto-scaling is cluster auto-scaling. So you have a cluster, you can scale the number of pods, but what if a pod cannot be scheduled because the cluster is too full? That's where cluster auto-scaling comes in, and we increase the size of the pool by adding VMs when necessary. And when there's not enough utilization on the VMs, we decrease the size, so it's both scale up and scale down. And again, that can be set up with a simple command specifying the minimum and maximum nodes that you want. I'm curious, how many of you are using any of these auto-scaling features today? That's great. Yeah, I hear very positive things about this. Cluster auto-scaling is beta, and we're adding a lot more features to support bigger clusters. So expect that to go GA in the next year. The final point around scaling is when you want to go to multiple regions. Currently, Kubernetes clusters can span multiple zones, and we'll talk about how to set up a multi-zone cluster in the next portion. But if you want to have a presence in another region, say, in Europe and in North America, and you want to have a local cluster in another region, then you go ahead and you set up a cluster in that region. With cluster federation, you can manage those two clusters, whether they're in different regions or actually in different clouds, from a single API. And that's done by setting up a federated control plane. And these are some of the things that the federated control plane offers. It offers an API that's very similar to the cluster API. In fact, it has all of the same objects. And in the upcoming release, we will be announcing support for deployments in the Federation API as well as for daemon sets. So that means that from one API endpoint, you can deploy across clusters in multiple regions or potentially multiple clouds. And we continue to add to that Federation API. The other things that the control plane does is check the health of the clusters and also offers geo-load balancing in GCP only. So while scaling and auto-scaling and federation have been a big part of what you've come to expect from Kubernetes, another thing that has been top of mind for many of our users is stateful applications. How can I run stateful applications in containers? Should I run stateful applications in containers? That's a common question. Dynamic storage provisioning is going GA in the next release. And we're going to talk about how to use stateful applications along with this. A common misconception is that containers are ephemeral and therefore, they're only good for stateless web serving applications. Kubernetes actually provisions the storage automatically for you, and with dynamic storage provisioning, it provisions the storage dynamically when a pod comes up, and it maintains and persists that storage until the application needs that storage. So let me talk a little bit more about that. How do you provision storage? One method is to specify in your pod spec that there's a volume and you'd like to have that volume mounted. And in this case, we say by name, what the volume is. It's a GCE persistent disk. Its name is Panda disk, and that's the type of file system it has. This is an okay methodology, but it's static. First of all, it assumes that the storage, the volume already exists. So someone has to pre-provision that even though the pod hasn't been provisioned yet. That's potential waste. Secondly, it's not portable. So if you were to take this pod spec somewhere else and that place didn't have a GCE persistent disk, then this is kind of useless and it would break. So the better way to do this is through a persistent volume claim. A persistent volume claim is basically a contract. And that contract doesn't name, now in the pod spec, a specific volume. Instead, it has a claim name. So this abstraction then allows Kubernetes to bind the PVC claim to the persistent volume, and then when the pod comes up and it requests the volume can be created. And this is an example of what the PVC looks like, the claim looks like. In the claim, you specify what type of storage you want. So in this case, we've said, it's 100 gigs of storage that I want, so the characteristics. And then another abstraction, which is the storage class. The storage class can be set by your cluster admin. If you're in a company that has a storage or cluster admin, and they are choosing what type of storage should be available to what type of applications, they may create a storage class, say a fast storage class that refers to SSDs, or a slow storage class that refers to a specific type of disk in a specific cloud. This separation of concerns allows for portability, and it allows for policy setting around storage. But what the real beauty of this is that it's actually dynamically provisioned. So when you instantiate or create your pod, the PVC gets created, and it's at that time that Kubernetes will go ahead and dynamically provision the storage. So it doesn't require that the storage is pre-provisioned. There's no wastage here. Also, you would set the policy in your default storage provisioner that when the PVC goes away, the storage goes away. So it also cleans up after itself. That's one of the nice things about dynamic storage provisioning. One thing I want to point out is that in our next release, while this is a nice set of abstractions, you've got, storage provider, you've got the user with the PVC claim, and you've got a cluster admin. Not everyone needs this level of separation, and Kubernetes does a nice job in our next release of just picking sane defaults for you. So pre-installed in the next version of Kubernetes and Container Engine, there are these default storage classes. In Google Cloud, it'll be a GCE persistent disk. In Amazon and OpenStack, these will be the defaults. And so when you don't have to, in fact, even say in your PVC that there's a storage class. This is the default class that'll be assumed. And when the PVC gets created, the storage automatically gets provisioned. So I'd like to actually demonstrate this. I think the most power of dynamic storage provisioning comes in when you use it with a stateful application. And I think if Kelsey is here, we might actually have a stateful application that can be used to demonstrate dynamic storage provisioning. Okay. Need a clicker?
We like live demos, right? All right, so I don't have any slides for you guys, so I apologize. And we're going to talk about this dynamic provisioning, but provisioning storage without an application to use it is kind of pointless. So we're going to deploy an app called Console. So if you've never seen Console, it's this key value store that has built-in replication and built-in high availability using Raft. And it also has a side communication channel using a SWIM protocol so that members can find each other even in the case of failures. So the recommendation for Console is that you run 3 nodes. Now, the typical deployment is each node has its own volume and is responsible for its own data set and will replicate between each of the members. So we want to deploy this in Kubernetes. Now, if you're doing this for the first time, you don't want to learn a particular cloud provider's way of provisioning storage and making sure that it's attached to the proper node in the cluster. So what we're going to do is work through this and see how you do it in Kubernetes. So the first thing we're going to take a look at is my current setup in my Google Cloud project. I'm only going to show you the disk, so compute disk list. So here you'll see that I can't spell at all. Just got to roll with it. So here are the disks that I currently have, and those are attached to my virtual machines. So when you think about this concept, you already see it for virtual machines. When you click on a VM, no one tells you to go provision a disk first to attach to the VM. You assume that the VM needs storage, that the cloud provider should create that for you. We're taking that and extending it to the application level. So this is how I want you to think about this when you see this in action. So now we need to describe our stateful set. So what I'm going to do here, there's a lot of content here, but we're going to highlight the important parts. So here I'm saying that I want 3 copies of this application. So what will happen here is Kubernetes will create node 0, node 1, and node 2. And the next thing we need to do is have storage assigned to it. So we're going to scroll all the way down to the bottom, and we're going to highlight this volume claim. Now here I'm using a template. Now the reason why I'm using a template here, I'm going to need Kubernetes to stamp out 3 versions of this. I'm going to have a request. Based on the documentation, I need about 10 gigs of storage per application. Console isn't designed to hold a lot of data. It's just there for your cluster configuration and your monitoring bits. And also, we don't really care what the storage class is. So if I was running this in a different cloud provider, ideally, the cluster running in that cloud provider would do the automated storage provisioning for me. So what we want to do now is submit this to our cluster. Now, we have some other bits that are already there, but we won't go through those. Things like configuration files and TLS certificates, so we can have a secure console cluster. But here we want to focus on the storage. So we're going to push this to our Kubernetes master. And while we do this, let's look and see what happens to the disk while this is going. So we'll just throw a watch there. So we see that we only have 3 disks, so we'll push this to Kubernetes now. So kubectl create-f stateful sets console. So this gets submitted to the cluster, and you see instantly it goes out and provisions the storage based on the needs of the operator. So now at this point, we can actually look at a few pods being created. So each of our applications comes up one at a time, and most of these kind of applications need to come up in a specific order, mainly because they need to form a quorum, and there's some bootstrapping phase. So node 1 is coming up. That's going to be scheduled by the scheduler to a particular machine. Once that decision is made, that volume will be then attached to that machine and injected into the container at runtime. Now, we'll do this a couple more times until we have the entire cluster up and running. So let's give that a few seconds and see where we are. So we have 2 out of 3. Let's do a watch here. All right, so this one's creating. Now, as this creates, we're going to actually go ahead and try to communicate with our cluster to see where we are. So here what I'm going to do is do a bit of port forwarding. I don't want you guys interacting with my cluster, so I'm going to do this over a private channel. So once I have this connection in place, I can start to interact with this console cluster. I can run things like console members. And you notice that there's only one member listed here. This is because they don't know anything about each other. They've all come up with their own independent storage volume, and they do not have the cluster membership configuration stored yet. We need to join the cluster. So what I'm going to do here, you got to raise your hand. Okay. Yes?
Can you show us the storage that's been dynamically created?
Good question. So in Kubernetes, what we have are, we talked about these volumes. So in Kubernetes, they're called persistent volumes. So if we say kubectl get PV for short, we can actually see those 3 volumes. And you'll notice that they're named some random name, but they're also attached to a claim. So if we list out the claim, the PVC, what you'll see is this convention. You'll see the data directory is the volume that I'm specifying inside of my manifest and where I would like it to be mounted, and also the name of the pod that it belongs to. So stateful sets gives your pods a consistent name, console 0, console 1, console 2. Now this is cool if you go up to 5 and you have to scale back down. We can configure our storage not to be deleted when our nodes or our pods go away, so that way if we scale back up, you're guaranteed to get the same disk that you had before attached to the same name. So you don't have to go around and worry about that. Okay, so this is what's happening underneath the scenes. Everything is bound to the right pods, and that will stay this way, and we'll see what happens if nodes go away. All right, so given that, what we want to do now is see what we can do about this cluster membership. So we have console members running, but we only have 1 member. So what we need to do next is form the cluster. Now what we're going to do is use a job here. So since we have consistent naming using stateful sets, notice here that I can reference all of my members by their DNS name. Now regardless of their IP address, this will resolve. So I'm just going to use the same console container. It's going to run the console join command using all 3 members of that cluster. So let's run this job now and see what happens. kubectl create-f jobs. So we're looking at our members here. We'll run the job. So this will go out and communicate to all the members. So if all of this is working, we should be able to see the console UI here. So let's check this out. So we see all 3 members, all help checks are passing. Now, why is this volume claim necessary? Why do we need this association to this particular pod name and its storage? Well, what happens if one of the pods goes away? So here what I'm going to do is delete one of our members. kubectl delete pods, and we'll give it this name. Now notice the IP address of this particular pod. The IP address here is 0.11. That's how all the other members know it as. And that particular member has inside of its storage directory the IP addresses of its other peers. So if it goes away, the only way it's going to be able to send signals back to its peers that it has a different IP address if it comes back with the exact same volume. So it's critical that we get the same volume if something happens. So we'll delete it here. And at this point, the heartbeats will time out, and this thing should go from alive to failed. And let's see if that happens. So now it's failed. Now what we expect Kubernetes to do is automatically replace this because we said that we want 3 of these. So if we look at pods, we see that it's automatically been recreated just 15 seconds ago, and now the storage is being remounted to the new machine. So what should happen is this machine should come up, grab its data volume, have information about the other members, and start to broadcast signals about its new IP address if it has changed. So we'll give this a few moments and see if we can actually have our cluster come back and have a full quorum ready to go. This is like what the demo guys are like, I don't know. Tick tock tick. Some people on the edge of their seats like, it ain't gonna work. I have confidence. I think I do. And it's back up and running. That's how you use dynamic provisioning with Kubernetes 1.6. Thank you.
Over to the slides. Thank you, Kelsey. So you saw dynamic provisioning, didn't need to have the storage there beforehand, and then the storage persists afterwards. The next feature, or the last set of features actually, that we're going to preview are related to scheduling. There's a number of advanced scheduling features that are coming in the next release, and these should help as you're provisioning larger clusters and provisioning clusters across zones. So first of all, we do recommend that clusters should be provisioned across zones because there is a likelihood or a possibility of a single zone going down. It's fairly easy to provision a cluster across zones. You essentially, when you create the cluster, you specify that you'd like additional zones, and it'll create nodes in those additional zones, and by default, the scheduler will spread pods across all the available zones in a cluster. That's nice. You can also do it once you've created the cluster and you want to edit it and add zones, you can also do that. That's nice, but there are certain things, when you're working with a cluster that spans zones that you might want to avoid. And that's where some of the custom scheduling and advanced scheduling techniques come in handy. One of these techniques is called node affinity. Node affinity is where a pod expresses a preference for a certain node. And it could be two types. It could be a preference or it could be a requirement. The node itself, would be specified, the characteristics of the node would be specified in the pod spec. So this is an example of a pod spec that is defining an affinity. It is a node affinity that says that it prefers a node that is in a particular region. In this case, it's US Central 1B. And that's done through, defining a operator that operates, and connects a key to a value. The key in this case is the zone of the node, and the value here that we're looking for is US Central 1B, and the operator is in, which is, I want the zone to be in US Central 1B. There are other operators, so it's kind of like a equation that you can set up, or a regular expression. Other operators that are supported are in or not in, so you could say not in this zone, or such and such exists, resource exists or does not exist, or is greater than or less than. Those are the operators that are supported. So what will happen here is that since we've expressed a preference and not a requirement, when the pod labeled app1 comes in and it has to be scheduled, it will have a preference to be scheduled in US Central 1B, and we have 3 nodes in our multi-zone cluster that are in US Central 1B. So if there's space available on any of those, it'll get preferentially scheduled there. It can still get scheduled in the other zones if there's not space available. Or you could make this a hard requirement if you, instead of use preferred, you use required. So that's node affinity. There are a number of built-in keys for nodes already. These are the built-in keys, so it could be zone, it could be region, it could be the host name, so you could say, I want a particular VM, and that's where it should be, or a particular type of VM. It could be a preemptible VM. You could say, I want these applications only to be run on preemptible VMs, and you would specify that here. And other things like the type of disk, whether it's SSD, what type of OS, But the best thing is you can also write your own. You can write your own, essentially, labels on nodes and then tell the scheduler, I want to schedule these pods on a node that has these labels. That's node affinity. A related feature is InterPod affinity. So now you want to specify where a particular application should be scheduled given where a certain other service is scheduled. This can be very useful. So again, we're talking about multi-zone clusters as an example. If you have 2 services that need to communicate with each other, say there's like an east-west pattern, and you don't want, those 2 services to be scheduled in different zones because then there's egress charges associated with that. Actually, the latency is very low in Google Cloud, but there are egress charges that you may want to avoid. So for ensuring east-west communication within zone, you can set the InterPod affinity. And this is an example of that. So this is a replica set, and there are 3 replicas, and the app name is app2. And what we would like is for this app2 pod to have an affinity to app1, to wherever the zone is where app1 is scheduled, we want app2 to be scheduled there as well. And in this case, we're not expressing a preference, we're saying that it's required. So we're saying here, pod affinity, required, and the operator again is in, and the value is app1, and the key is zone. So now we want app2 to be co-scheduled in the same zone so that east-west communication is less expensive. There are other use cases, of course. It also works if you want to co-locate north-south services. And then there's also anti-affinity. So affinity is when you want two pods to be scheduled together. Anti-affinity is when you want to spread pods across, or you want to spread your services across your cluster. This could be because you have some antagonist pods that you want to keep separated, or you want sole tenancy, or a variety of other use cases. So this is the other advanced scheduling capability that's going to be available in this release. The third one, which I think is perhaps the most interesting one, is this concept of taints and tolerations. And this is where it's not really a single pod or a single set of services that you want to set rules on, but a whole set of services that should avoid a particular node. Or then what you do is you taint the node. You put a taint on the node, and then you put a toleration on specific pods that should tolerate that taint. So an example is, here we have a node that has, 2 GPUs, whereas the other nodes do not have GPUs. So we can put a taint on that node that says, and that's how you do it, kubectl taint node, GPU true, and so it prefers no schedule. So do not schedule on this one because it's a GPU node and it's maybe more expensive or special. And then the application or the pod that actually requires GPUs, you would put a toleration on that one that says the key is GPU, and I have a toleration for that. So when that pod comes around, it'll be scheduled to node 1, but every other pod will avoid that tainted node. This is, very similar to affinity in that you could use required or preferred and so forth. But where this is really interesting is in what is called a feature that we call forgiveness, where you put a taint on every node that says, you should evict all running, you should stop and evict all running pods in the case of, say, node becoming unresponsive or disk not being available in the case of a failure. If the node fails, stop the pods and evict them. And then you can put a toleration on the pods themselves that says, how long should this pod remain on this unresponsive node? When should it get rescheduled? So this is a really nice feature that actually recently had a very good use case. When there was an outage, S3 outage on AWS last week, there's a company, I think they're called, I always forget their name. I think they're called Stripe, or anyway, there's a company that was using this feature, and when their nodes became unresponsive, their pods automatically got rescheduled because the disk wasn't available on that node. Their pods had this toleration, and after a certain amount of time, they automatically got rescheduled to a node that did have space available. So those are some of the advanced features that are coming. The last and not least one is the ability to set up a custom scheduler. So all of this gives you a lot of flexibility to deploy the way you want to, but you're not limited by the default scheduler. You can actually bring in your own scheduler and extend Kubernetes to use whatever rules you want to have. Let's see, maybe Kelsey has a demo of a custom scheduler as well.
Hell yeah, I have a custom scheduler. All right, so Aparna talked about this ability to give your nodes attributes, ad hoc attributes. We call them annotations. So on each nodes, if you look at them, if you were to list our nodes in this cluster, have 3 nodes in our cluster. And what we can do is get a little bit more info about them. So if I say -o equals YAML, we get a bit more data about these nodes. And here we can actually see different attributes, labels, annotations, and so forth. Now, given that we have things like region and zone, I want to build a custom scheduler that lets me choose the node based on the cheapest price, okay? So all these nodes may have different attributes, but hey, what I want to do is favor the cheapest nodes first before moving on to the next node. So one thing we need to do is annotate our particular nodes. So I have a little tool called Annotator, just goes out to the Kubernetes API and writes annotations on them based on their price. So we'll run this, and we see that one of the nodes is 10 cents per hour, 80 cents per hour, 40 cents per hour. So ideally, any workload that I execute, I want to run on A-B, or A to B, 1B, okay? That's the goal. So what is it required to actually run multiple schedulers in Kubernetes? Well, you need to do a little bit of things different. So here, we're going to take a deployment object. So these deployments run inside of Kubernetes, and by default, the default scheduler pulls them and runs them inside of your cluster. Now, let's say you want to use a different scheduler. Here is an annotation on my workload, in this case a deployment, And here, I'm using a custom scheduler by name. Now, normally this would be default, but when you get to this level of Kubernetes, you get to have a scheduler named after you, if you want that. So this is the Hightower scheduler. And the Hightower scheduler will pick nodes based on price. So when this workload gets executed, it will be ignored by the default scheduler. That's the key here. So these schedulers get to run in parallel inside of Kubernetes. So I'm going to run this workload, and you notice here that we do have CPU and memory requirements. So those two predicates can't be ignored just for the cheapest price. We need to run on the node that also fits our workload. So what I'll do here is deploy this workload. Nginx custom. So at this point, we now have a pod running. So we'll actually show that here, kubectl, get pods. And we'll throw a watch there. So notice here that it's sitting there pending. How long will this pin? This will pin forever, actually, because there is no scheduler running inside of the cluster that knows what to do with this. It's being ignored by the default scheduler. Only thing that we have at this point is our desired state that it should be running somewhere, but there is no scheduler that's in charge of this. So I wrote my own scheduler. It's on my laptop. It's also available on GitHub if you want to check out the code. So here I'm just going to build the scheduler. And I'm going to now have my scheduler point at my Kubernetes cluster and schedule this particular workload. So here we'll just run it. So we're starting our scheduler. And notice here that we scheduled this particular pod to this particular node. I'm going to remind you guys of the price of these nodes just to make sure that we landed in the right place. So we just do annotator-L again, and we notice that this was the cheapest price. So this is where we expect it to land. And there we go, it's up and running. Now, if I were to scale this out, I expect the same behavior. Prefer the cheapest node until your workload no longer fits before you spill over to the next node. So let's scale this up a little bit to see how that works. So what we'll do is say kubectl scale deployments, and this is going to be Nginx custom. And then we're just going to give the replica set. What number should we go up to? 42. Round it down to 40. Divide by 4 is about 10. So we'll do that. So we have 10 of these things running now, and we'll see what our scheduler does. So it's continuously preferring the cheaper node. Now, eventually, that node will no longer be able to host our workload, so we may have to spill over to the next node. Ideally, we're going to spill over to the cheaper node. So there we go. It's automatically moved on to the cheapest node. So my scheduler is doing the right thing. It's continuously running and binding things based on that last predicate that I defined on my own. So the next question is, how do you actually get this scheduler to run inside of Kubernetes? So we're going to kill it from our laptop. And now we need to deploy it to Kubernetes itself. So, of course, we need a deployment object. So here we have a scheduler object, and it needs to run as a pod itself inside of the cluster. And if you've guessed it, we're going to use the default scheduler to schedule our scheduler so we can have parallel schedulers in our cluster, okay? So let's see if this works. So we see we have some custom workloads there. So we'll say kubectl create-f deployment scheduler. And at this point, our scheduler will be scheduled by the default scheduler, and now we have parallel schedulers running in Kubernetes. Thank you.
That's great. Thank you, Kelsey. So that concludes the demos and the features that we're going to announce. There's a few more features, obviously, and there's a much bigger roadmap. There were other talks at the conference yesterday and today that talked about auto upgrades and auto repair in Container Engine. That's something that is launched as beta as of this conference. And then, we are also going to be introducing RBAC, role-based access controls, as beta, and network policy is already beta. And then container runtime interface will be going beta as well in the next release, which allows you a choice of different runtimes. These are some of the related sessions, but what I'd like to do now is to open it up for Q&A and to invite George and Kelsey to come up and join me on stage for your questions.
Could we give a round of applause for Aparna for an awesome presentation?